On a stormy January morning in 1995, a single wave rose from the North Sea like a moving mountain. To the engineers on the Draupner platform, it was not just another storm swell. This wave was over 25 metres tall, more than twice the height of the waves around it. It was the first instrumentally recorded rogue wave, and it changed ocean science forever. For centuries, sailors whispered of walls of water that appeared without warning. But science dismissed these tales as exaggeration. The common belief held that the tallest waves were simply the peaks of a storm, nothing more. The Draupner wave proved them wrong. So what makes a rogue wave different? It's not just size, it's how it forms. Unlike storm waves that build gradually, rogue waves can appear from calm seas, born from the alignment of multiple wave trains, or the focusing of energy by ocean currents. They are a different beast entirely. For centuries, sailors told stories of towering waves that appeared without warning, rising like mountains from a calm sea. Their accounts were dismissed as exaggeration, the fantasies of superstitious men. Science had no room for such anomalies. The sea, it was believed, obeyed predictable rules, but the ocean had other plans. So why did science refuse to believe? The problem was simple. No instrument had ever recorded such a wave. Without data, the stories remained anecdotal. Oceanographers assumed the tallest waves in a storm could only reach about 15 metres. Anything larger seemed impossible. But the ocean does not care about our theories. And in 1995, a single sensor on a North Sea platform would capture something that shattered the old assumptions forever. The age of the rogue wave had begun. So how did science finally prove that rogue waves were real? The answer came from an unlikely source, a single sensor on a gas platform in the North Sea, on a day that began like any other. On January 1st, 1995, at 3:20 p.m, a laser rangefinder recorded a wave of 25.6 metres, more than twice the surrounding sea's significant wave height. It was the first time a rogue wave had ever been measured by an instrument. What made this measurement so crucial wasn't just the height, it was the context. The sea state was not extreme, the significant wave height was only 12 metres. This wave was a statistical anomaly, a freak that defied the models. That single data point shattered decades of scientific skepticism. If a rogue wave could be measured once, it could happen again. The question was no longer if, but how often and where. What physical processes concentrate ocean energy into a single devastating pulse? After Draupner, oceanographers identified three mechanisms: constructive interference, current focusing, and nonlinear focusing. Each is a different way the sea can build a monster. Consider the Draupner wave itself. Analysis showed multiple wave trains travelling together. When their crests align, they combine, like two ripples merging into one. This constructive interference can produce a wave far taller than any individual component, exactly as happened that January day. But there's a second, more insidious mechanism: current focusing. When a wave meets an opposing current, like the powerful Agulhas Current off South Africa, it slows down, its wavelength shortens and its height grows. The current acts like a lens, bending wave energy into a single towering peak. The most mysterious mechanism is nonlinear focusing, or modulational instability. In deep water, a group of waves can spontaneously steal energy from its neighbours, focusing it into one colossal wave. This is not simple addition. It's a violent redistribution of energy, like a crowd surging forward, leaving gaps behind. So which mechanism created the Draupner wave? Analysis later showed it was likely a combination: a moderate sea state with multiple wave trains, plus a slight current, all aligning in a perfect storm of chance. The ocean had simply arranged its energy into a single, monstrous pulse. So the Draupner wave had proven rogue waves were real, but was it a one-off anomaly, or were these giants lurking across the world's oceans? The answer would come from an unlikely vantage point: space. Between 2001 and 2003, the European Space Agency's MaxWave project analysed 30,000 satellite radar images. The result was staggering. Over 10 individual rogue waves taller than 25 metres were identified, scattered across the globe. One hotspot stood out: the Agulhas Current off South Africa, where opposing currents can focus wave energy into monsters. The old sailors' tales of sudden towering walls of water were not exaggerations. They were understatements. So, if rogue waves can appear from nowhere, how rare are they really? The old assumption was a probability of 1 in 10,000 waves, but satellite data from the MaxWave project revealed something startling. In certain conditions, that number jumps dramatically. The Agulhas Current off South Africa is one such hotspot. Here, waves moving against the current can compress and steepen, turning a 1 in 10,000 chance into something far more common. The ocean's hidden teeth are not evenly spread. So the old assumption of one rogue wave in 10,000 waves was shattered. But what does that mean for the ships that sail these waters? The ocean does not follow our statistics, and modern vessels must be built to survive what it throws at them. Classification societies like DNV and ABS set rules for hull strength, requiring ships to withstand wave loads calculated from a design wave with a 20-year return period. But rogue waves can exceed that. One naval architect put it bluntly: "We must design ships that can survive the unexpected because the ocean does not follow our statistics." So modern ships incorporate structural reinforcements, thicker plating, stronger frames, to handle loads up to 10 meganewtons per square metre. Yet even these measures cannot guarantee survival against a wave that defies probability. The ocean's hidden teeth remain sharp, waiting for the moment when design meets the unexpected. But to understand rogue waves, we must first understand the sea's energy spectrum. A storm generates waves of many different wavelengths and speeds, each travelling independently. Most of the time, they cancel each other out, but occasionally they align. Constructive interference is like a choir singing in perfect unison. When two wave crests meet, they add up to a wave twice as high. But extreme waves can involve 3, 4, or even more wave trains aligning at once, creating a towering peak that dwarfs the rest. Current focusing is even more dangerous. Off the coast of South Africa, the Agulhas Current flows south at up to 5 knots. Waves coming from the south collide with this current, their energy compressed into a steep, towering wall that can appear without warning. Nonlinear focusing or modulational instability is the most mysterious. In deep water, a group of waves can spontaneously steal energy from its neighbours, focusing it into one colossal wave. It's like a crowd surging forward, leaving gaps behind. Satellites use radar altimeters to measure sea surface height across vast swaths. The MaxWave project analysed 30,000 such images, each covering hundreds of kilometres. They found rogue waves in every ocean, not just the North Sea. The data revealed hotspots: the Agulhas Current off South Africa, the Gulf Stream, the Kuroshio Current, and the Southern Ocean. These are regions where strong currents oppose prevailing winds or swells, creating conditions ripe for extreme waves. Modern ships are designed to withstand a design wave with a 20-year return period, but extreme waves can exceed that by 50% or more. Classification societies now recommend additional strengthening for ships that frequent known hotspots. So we've mapped their haunts, measured their height, and named their mechanisms. Yet the ocean still keeps its secrets. An extreme wave can rise without warning from a calm sea in any moment. The sailor's saying holds true: the sea hides her teeth until the worst moment. But what does an extreme wave actually feel like? Survivors describe a sudden, violent lurch, as if the ship has been punched from below. In 2001, the cruise ship Bremen was hit by a 30-metre wave in the South Atlantic. Its bridge windows shattered at 60 metres above the waterline. So can we predict these waves? Today, machine learning models trained on wave buoy data can forecast the probability of an extreme wave minutes ahead. But the ocean's chaos still defies certainty. The best we can do is warn ships to alter course. Which brings us to the most unsettling truth. Rogue waves can form even in relatively calm seas. The Draupner wave itself rose from a sea state that was not extreme. The ocean's hidden teeth are not always bared in a storm. So the science has mapped their haunts, measured their height, and named their mechanisms. Yet for all our instruments and models, the ocean still keeps its secrets. An extreme wave can rise without warning, from a calm sea in any moment, and the sailor's saying holds true: the sea hides her teeth until the worst moment. We sail on knowing that beneath the surface, the hidden teeth remain.